Okay, balancing redox equations. This video explains how to balance redox equations by the oxidation number method. We will use a second method, the half reaction method. That's coming up in the next video. All right, there are 12 steps. I recommend you write these down, and then we'll go through some examples together. Okay, so here's example 1. You'll notice that I have written out this example with space on the left side of the equation and also on the right side. As these equations get more complicated, sometimes we add entities like water or the hydrogen ion or hydroxide ion to the left and right sides of the equation. And so if you start writing your original question at the far left side of your page, you haven't really left space for that. So I'll just emphasize that that's how I wrote this example to start. Okay, step number 1 is to assign oxidation numbers. So we're assigning oxidation numbers to every atom in every entity, reactants and products. So hopefully you have already mastered and practiced how to do that. That was covered in lesson 1 of the unit. And so go ahead and assign oxidation numbers to the reactants and products here. Okay, so the iodide ion, a single atom ion, monatomic ion, the charge is the same as the oxidation number, -1. Cl2 is a diatomic element. Being an element, the oxidation number is 0. Chloride ion, charge of -1, oxidation number of -1, and elemental I2 gets a sign of 0. Okay, now we track the gain or loss of electrons per atom. And so I'm looking at the iodine here and noticing that it changes from -1 to 0. So if we're down at -1 and moving up, then the oxidation number is getting more positive, which is the same as getting less negative. And so electrons are being lost. This was our oxidation pattern. And so we'll say that lose 1 electron here per iodine, so per atom. This is step 2. Also, we look at the Cl2 and notice in going from 0 to -1, so from 0 down to -1, this is reduction. Leo goes Gur, there's a gain of electrons. In this case, from 0 to -1 is 1 electron, and that's 1 electron per chlorine, per atom. So that's step 2. Step 3 says to adjust this now for the gain or loss from per atom to per reactant. So I gave you the steps in red here. Multiply the number of gained or lost per atom by the number of atoms in each reactant. And so I'll show you here what I mean. We see that there's 1 electron loss per iodide, and we're trying to state the number that are being lost per iodide ion. Well, in the formula of the iodide ion, the subscript here is 1. So if 1 electron lost per iodine, and there's only 1 iodine in this reactant, then 1 times 1, there's just 1 electron being lost per iodide. That might have been obvious to you and even sound confusing when I explain it, but let's look at the second reactant here and see if this helps clarify it. We're saying that the oxidation number for chlorine is changing from 0 to -1. And so there's a gain of 1 electron per chlorine atom. But now we need to state it per reactant particle. The full reactant particle there is Cl2. So what's the gain per Cl2 molecule? If it's 1 electron per chlorine, and there's 2, a subscript of 2 here, then 1 times 2, there are 2 electrons being gained per chlorine. And so that's step 3 in our series of steps, and that's a really critical step. I find if people make mistakes, it tends to be right there. So you need to catch that. You need to be sure that you multiply the number that's being lost or gained by the subscript in the formula of the reactant. And in the case of chlorine here, it was Cl2, and that's why we had to double the 1 electron. Okay, moving on. Now we're going to move on to step 4 and determine the multipliers so that the total electrons lost equals the total gained. So we're saying there's 1 electron being lost per iodide here and 2 electrons being lost per chlorine. So what is the lowest common multiple then of 1 and 2? Well, hopefully you're thinking 2. And so what are the numbers that we need to multiply Well, here it's 2 and here it's 1. So I'll just remind you that when we balance equations, we can't change the formulas. We just put numbers onto the blanks in front, the coefficients. And so it's these multipliers, as I said in the steps here, the multipliers are the coefficients. And so it's these multipliers that I wrote in green, that get brought up to the coefficients in the equation. Now we're finished with all of this work right here. Okay, and now we're focusing in on step number 5, balancing all atoms except O and H. So 2 times 1, there's 2 iodine here, and we come over here and see that there are 2 iodine there. And so that would fix a coefficient here at 1. If we look at the chlorine here, 1 times 2, there's 2. So we come over here, and having only 1 there, we need to put a coefficient of 2 here. Okay, following the rest of the steps, number 6, we add water to balance oxygen. Well, in fact, there is no oxygen in this question, and so oxygen's already balanced. It's not even present. Moving on to step 7, we add H positive to balance the hydrogens. Well, again, there are no hydrogens, and so there's nothing to do. So we reach step 8 and check for mass and charge balance. So the mass, checking that mass is balanced, you're really checking for the number of atoms. This is what you learn to do in grade 10 when you learn to balance equations. So the fact that there are 2 iodine on this side and 2 over here, iodine is balanced. 1 times 2 here for the chlorine, and 2 times 1, we have 2 chlorine on either side. Now let's check for charge balance. So look at the coefficient and multiply by the charge on this particle, if there is a charge. So iodine has a charge of -1. So if there's 2 iodide ions, then that's a charge of -2 in total. Here, Cl2 is neutral. 1 times 0 is 0. Then we reach the arrow. So on the left side here, the overall charge is -2. I'll put that down here in blue. So I've got -2 there. Now I look at the right side. I see 2 times this -1 charge, so there's -2, plus 1 times 0. I'm looking at the overall charge of this product particle, and I2, what I wrote in blue, the original equation, the original product here, has no charge, so 1 times 0 is 0. And so we come up with a charge of -2 overall on the right side. So what matters is that this charge, this overall charge on the left side and the overall charge on the right side is the same. And that's how we check that it is balanced, the equation is balanced for charge. So an equation needs to be balanced for both mass and charge to be balanced. Okay, we didn't have to do the steps involving water or hydrogen ions or hydroxides, so we'll come to those in more complicated examples, but see if you can then do steps 1 through 5, which is really what we had to do in example 1. See if you can do steps 1 through 5 on your own for example 2, and then check in with the video and we'll pick it up from there. So I realize you can't see example 2 yet. I'll jot that down quickly for you and then you can try it yourself. Okay, so here's example 2. Again, you'll notice that I didn't start immediately at the left side of my page, just anticipating that I may need to add in some entities. So try to run through steps 1 to 5 yourself here and then check in with the video. Okay, so assigning oxidation numbers, I ran across the top here. Chlorine at +7, oxygen at -2, bromide at -1, bromine here at a -1 in the bromide ion, -1 for the monatomic ion of chloride here, +5 for the Br, and -2 for oxygen. So reminder, this bromide ion has a -1 charge. So if you are solving for x, 1 times x plus 3 times -2 equals -1. And that's the same thing for the perchlorate ion. Okay, so that turned into +7 becoming -1. And so that's a gain of 8 electrons, 8 places on a number line. That's per chlorine, and because there's only 1 chlorine, that's 8 electrons per perchlorate ion. For the bromine here, the oxidation number changes from -1 to +5, +5. That's actually 6 units on a number line. So we have a loss of 6 electrons per bromine, which again, because of the subscript of 1, is 6 electrons per bromide ion. So now I look at the 6 and the 8, and I need the total electrons lost and gained to be equal. The lowest common multiple of 8 and 6 is 24, and so 6 times 4 is 24, and 8 times 3 is 24, and I carry those multipliers up to be the coefficients. And from here, I do step 5 where I balance the chlorine. So I see 3 chlorine on the left, so I'll come over here so that 3 times 1 here is 3, and 4 bromine, so I come over here, and 4 times 1 would be 4. Now we need to check oxygen. So we look at the oxygen on the left side, 3 times 4 is 12, and then come over to the right side, 4 times 3 is 12. So again, we do not have to add any water to balance the oxygen, and therefore no hydrogen ion, and so we can check for mass and charge. So 3 chlorine, 4 bromine, 4 bromine, 12 oxygens, and now we check for charge. And so we have 3 particles here with a -1 charge each, that's -3, and 4 particles here with a -1 charge, so that's -4. So we have -3 plus -4, so there's -7. And on the right side, 3 times -1 there is -3, and 4 times -1 is -4, and so we finish up with a charge of -7, which is the same as what we had on the left side. So when the charge on the left side and the right side are equal and you're balanced for mass, then we have fully balanced the equation for both charge and mass. Okay, it's about time we did an example where oxygen did come into play. So just a moment and I'll get example 3 on the page for you here so that you can try that. Okay, so again I'm leaving space on the left side and the right side of the equation. So go ahead and try steps 1 through 5, then check back with the video. Okay, and so I assigned oxidation numbers and noticed that the chlorine was changing from +5 to -1, which is a gain of 6 electrons. And because there's 1 chlorine in the chlorate ion, that's 6 electrons per chlorate. Here, +4 changes to +7, that's a loss of 3 electrons, and so manganese is losing 3 electrons per Mn, which, because there's the subscript of 1 here, 1 times 3 is 3, so 3 electrons per manganese dioxide particle. Lowest common multiple of 6 and 3 is 6, and here we're multiplying by 1 and here by 2. Those become our coefficients. Making sure that there's 1 chlorine on each side, I need a 1 here, and 2 manganese, I need a 2 here. 2 times 1 is 2. Now we move on to step 6 and check the oxygens. So 1 times 3, there's 3 oxygen here. 2 times 2, there's 4. So 3 plus 4, there's 7 oxygen on the left side, and I come over here and see 8 oxygen on the right side. And so this will be different than anything else you've ever done, but what we're going to do now is add water to balance the oxygen. Now, why did I add it to the left side? Well, think about the fact that we're trying to balance the oxygen. Here we had 3 plus 4 is 7. So if I put 1 water molecule here, then I've effectively added 1 oxygen to the left side. Isn't that what I needed? 1 plus these 3 is 4, plus these 4 is 8, and that will equal to 8 on this side. So 8 oxygen here, 7 oxygen here, plus this 1 now gives us 8, and so we're equal on the left and right. Now you notice by adding water that I introduced hydrogen into the equation. And so here we now have 2 hydrogens on the left side and none on the right side. So here's where we go then to balance for hydrogen. So we add 2 of the aqueous hydrogen ion. And so now in doing that, if we were asked to balance this equation in acidic solution, then we should be finished. Once you've added the hydrogen ion, you've introduced an excess of hydrogen, the solution is acidic. So let's check that it's balanced for mass and charge. So 1 chlorine, 2 manganese, 2 manganese. 1 oxygen plus these 3 is 4, plus these 4 is 8, and over here we have 8 oxygen. I see 2 hydrogen on the right, come back and there's 2 hydrogen on the right. Now check charge. Water's neutral, so 1 times that neutral, 0, is still 0. 1 times -1 is -1, and this was neutral. And so we just have a charge of -1 overall on the left side. Checking the right side, 1 times -1 is -1, 2 times -1 is -2, so we've got -1 plus -2, and 2 times +1 is +2. And so we had -1 plus -2 plus +2, and so you'll see when you add these integers, you end up with -1. And so the equation is balanced for charge also. Okay, the last example is example 4. We're going to balance this one in basic solution, which means that we'll take it through for the entire series of 12 steps. So jot example 4 down and see if you can take it through, at least up to and including the acidic hydrogen ion step, and then check back with me and we'll take it through to base. Okay, I'm not quite finished, but I thought I would, before it gets too far along, start showing you what I've done here. So the TE, I assigned the oxidation numbers for TE, oxygen, and so on, and notice that the TE is gaining 4 electrons. That's per tellurium atom, and there's one of those in this particle, the reactant particle, and so we have 4 electrons for this reactant particle. For nitrogen, it's changing from +4 to +5, and so that's 1 electron being lost per nitrogen. Because there are 2 nitrogens in the formula, 2 times 1 is 2 here. So it's 2 electrons per N2O4. Lowest common multiple of 2 and 4 is 4. My multipliers here are 2 and 1, and they become the coefficients. Now there's 1 TE, 1 TE. 2 times 2 is 4 nitrogen, so 4 times 1, there's 4 nitrogen. Now I check oxygen, 12 over here, 8 plus 3 is 11, so I need to add water on the left side in order to balance the oxygen. And in doing so, I now have introduced hydrogen. I see there's 2 H's here, none here, none here, so 2 H's on the left side, which means that I'm going to need to add hydrogen ion to the right side. Now how many of those do I need to add? Well, 2 to balance the 2 that are on the left side. Now, if this equation were requested in acidic solution, then we'd be finished, but we're actually going to balance this equation in base. It helps to check if you're balanced for mass and charge at this point, because if you're not, then the mistake has come earlier and you want to fix that before you move on. We're balanced for mass, the number of atoms are good. Let's check the charge. Water's neutral, 1 times -2 is -2, and this is neutral. So we're looking at a -2 charge overall there. And then neutral here, 4 times -1 is -1, and +2 there. And so we have -4 plus 2, which is -2. So you can see that we're balanced for charge right now. Okay, now we go ahead and finish the last few steps. We add hydroxide ion to both sides of the equation, because at this point the equation is balanced. So we add hydroxide ions, and I'm a little bit out of space there. So we're adding hydroxide ions to both sides of the equation over here. Oops. And how many do we need to add? Well, enough to neutralize these 2 hydrogen ions. So that means we'll add 2 hydroxide ions on both sides here. Oops. It's a little bit tricky to fit that in. There's 2 hydroxide there. Okay, now we simplify for the neutralization reaction of the hydrogen ion and the hydroxide. So we have 2 hydrogens and 2 hydroxides, so those will essentially form 2 water particles. And now we need to check and see about the water particles we have on either side. So notice here on the left side we have 1 water particle, and over here we have 2. So if we collect like terms, we'll swing this water particle over here and subtract it. And so we can cancel this water particle here, and now we'll have 1 left on this side. And so to balance, or we should be finished at this point, but to write this out so that we can check, and so that somebody reading our work could actually understand what we've written, we essentially at this point have 2 hydroxide ions, the water canceled there, plus this TeO3 2 negative ion, and there's only 1 of those, plus 2 of the dinitrogen tetroxide, and that's forming the tellurium, plus 4 of the nitrates, plus 1 water. And so this is in fact our final answer, having shown the work up above. So let's check that we're balanced for mass and charge. So looking at oxygen here, there's 2 here, plus these 3 is 5, plus these 8 is 13. We come over here, 4 times 3 is 12, plus 1 is 13. Perfect. 2 H's, 2 H's. 1 Te, 1 Te, 4 nitrogens, and 4 nitrogen. And now to be balanced for charge, we have a -2 here, plus 1 times -2, so we're at -4, and that's neutral, and so we are here at -4. And on the right side, neutral, this is -4, 4 times -1, and this is neutral. And so we're finishing with a -4 charge on the right side. And so you can see that we're balanced for both mass and charge.